Welcome everyone to the 2024 Vision Spectra Conference. Thank you all so much for joining us. And in this session, you will hear from Ronian Su, an optical consultant with more than 25 years of experience designing optical systems. Ronian earned degrees in optics and physics from the University of Rochester, wrote 4 books, and holds 2 patents. Today, he'll share a way to achieve top hat illumination uniformity with a single source. If you have any questions or comments, you can type them right into the conference chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. That's all from me, Ronian. We appreciate you taking the time to present at the 2024 Vision Spectra Conference.
Thank you very much, Jake. Appreciate that. Let me open up my slides here. All right. Thank you again. And hi, guys. My name is Ronian, and today I'll talk about uniform top hat oblique illumination for machine vision applications. As Jake mentioned, I have 4 books, and on display here are 2 of the most popular books. And the reason why I've got this here is because as we go through the slides, some of the material in the slides are examples taken from the books. And if the audience wants to know more about those examples, you can go to the books and read more about them. So as mentioned, I'm a consultant at the Venture Biotech Modules business. I specialize in advanced precision control technology solutions, and that means it makes modules like these. And it is a spinoff from a larger corporate called Venture Corporation Limited. For more information, you can go to the website vbmb.com. All right, so without further ado, let's talking about the presentation material. Okay, so in machine vision, there are many types of configurations used for illuminating the region of interest or sample of interest. Some of the most common type of configurations are shown right here. There's the so-called dome coaxial, and interestingly, I'm not totally sure why it's called coaxial, but I think the reason is because the illumination is, I guess, concentric to the alignment between the camera and the object being of interest. And in this particular case, you've got a dome that is reflective, a diffuse reflective, and over here you can put a light source, such as an LED or 2 or multiple LEDs, and you shine the light onto the dome, and the dome reflects the light diffusely onto the object. Right, so it's a kind of way to mimic ambient lighting. Everyone knows if you go to a room, you turn on all the ambient lights in the room, and you're reading a book or a page from any source, and pretty much the entire page is uniformly illuminated. That's because you've got light all over the place in a room. And this dome here kind of simulates that in a local sense. Instead of having the whole room lit, you just have this dome lit, right? And then backlighting is, well, if you're looking at your computer monitor and if you're using a liquid crystal display monitor, then you've got a backlight behind a number of liquid crystal pixels. So it's basically that. But if you've got a transparency for an object that you're trying to illuminate, you can put any kind of lighting behind and put maybe a diffuser to kind of scatter the light, and you can look through the object and put the camera on top, and that's what's called backlighting in machine vision. And then oblique dark field, they call it kind of dark field because you don't see the source. You put a light somewhere behind the camera or somewhere in the side, and you put 2 of them because you want to have some symmetric illumination, right? So that's kind of called oblique dark field. And in machine vision, it's very much like illumination or lighting in microscopy, where you are trying to put together all kinds of configurations in illumination in order to see what you get the most out of the sample. In microscopy, that's the way it is. In machine vision, you would try all methods to just kind of extract as much information as possible from the region of interest. So all kinds of lighting could potentially work. If you are new to machine vision and you need a light source, you normally choose several and try them out. If you have to use any one of the configurations to see anything of particular interest you want, you would in fact use any one of those configurations. So that's why there are many kinds of configurations in machine vision lighting. So speaking of dark field lighting, there are also variants. You can put a ring of LEDs around. You can put planar sources, linear sources. The basic point here is you want to kind of create a sort of uniform illumination across the field of view. For example, if you put a string of LEDs around the camera, then all the light from each LED will kind of homogenize the object in a symmetrical sense. If you just put half of a ring, then usually one side of it will be brighter and the other side will be darker, right? So you put a string of LEDs around in a ring form, you'll see the object. Now there's a trick involved in this as well, as I'm going to talk about in the next slide. But the basic idea is to homogenize the region of interest. Then you could put planar light source. A plane. What is a plane? Well, you could have an array of LEDs in a square or rectangle. You could put fluorescent tubes in a line format across the plane, and you put 2 of them here so that you get the symmetry. You can put 4, 1, 2, back behind the camera, in front of the camera as well. Linear source will be maybe 2 fluorescent tubes of the old-fashioned type. You can do that, or a string of LEDs in a ring. I mean, in a line. So all of these are an attempt to kind of homogenize the illumination on the object. But as I mentioned, if you're going to put any kind of source surrounding the camera, you have to consider one thing, which is that depending on the height of the source and the distance, the radial distance between the source and the camera, you may see the source in the camera. And the basic reason is because if, let's say, you've got an LED right here and it's shining a ray down at with this angle and reflects off a smooth surface somewhere next to the object, it can bounce off that surface into the camera, right? And that happens if the source is within the field of view of the camera. And those of you who are lens designers who are dialing into this conference, you'll kind of know this. If in fact the field of view of the camera is within this cone angle, then anything within this region is viewable or seeable in the camera. So how do you determine how far away must you put the source in order to not see the light source, to see the glare? That's called glare, right? Well, then if you're a lens designer, you can take your camera, your imaging lens in the camera and reverse trace the chief ray. This is called the chief ray. From the entrance pupil of the camera back outwards, bounce it off a surface out to here, and you'll get what I call a glare radius. And by simple trigonometry, the glare radius is given by 2h tan theta over 2. Right? If you're not a lens designer, you can do this by trial and error. You situate your camera above the object, and then put the light source away. And if you put it right next to the camera, you'll see the light source. If you've got a non-diffuse surface on the object, if you got for example, like a glossy magazine cover that you're imaging, you will see the light source. Of course, you can put polarizers, but that will make the whole scene darker. But if you put the light source farther and farther and farther away here, you'll see that at some point you won't see the light source, and that is your so-called glare radius. So this is talked about in my book, Modern Classical Optical System Design, in page 3-46. If you want to know more about this, you can look into there. All right, so that is the criterion to avoid glare when you put ring LED illumination. All right, but in some instances, you may want to have just a single light source. For example, perhaps you may want to have space on one side of the camera to mount other useful components. In that case, you will only have one space to put your light source. Of course, you could put sources in and out of this page, but what if you want that space for other things as well? So you have only one space to put your light source, and it'll be an oblique angle, obviously, to point towards the object. And there's also a trick there involved as well. You can't just point the source to the object, and I'll tell you why in a minute. Secondly, if you have a single light source, you could, of course, you could, if you want to have different colors illuminating the object, you could put different LEDs in the same small section, but then you'll only have those LEDs, right? What if you've got a white light source with a broad spectrum, and you want to switch colors. You can put it on, well, you can put the filters on a filter wheel. And if you're not happy with these colors, you can always switch out the filters, right? So there are advantages to having just a single source and at an oblique angle. But the problem is that the irradiance or the flux density, the flux per unit area, flux density, we call it irradiance in technical terms, across the plane of illumination, it's going to vary because the irradiance is going to be proportional to 1 over r squared and the cosine of the angle. What happens, therefore, is that rays that are closer, not rays, but points on a plane that are closer to the light source are going to be brighter, and points farther away are going to be darker. And not only that, you've got the cosine theta as well. So you're going to have this weird asymmetric distribution, which you may not like in machine vision or any type of illumination for that matter. So you've got this issue here. How are we going to deal with this issue if you've got one source and this asymmetric profile, which we can call an asymmetric profile a non-uniform profile, but even though it's symmetric, it can be non-uniform, but it's more uniform than asymmetric, right? So our first goal is to create a uniform distribution across, not a symmetric distribution across the plane with just a single source. How are we going to do that? Well, if you go to my other book, Perspectives of Modern Optics and Imaging, in equation 3.13, figure 3.20 in that book, you'll see me sketch out a diagram such as this. Let's say you've got a tiny source, an LED, that has a Lambertian emission. Lambertian means this. If you go to an LED data sheet, you'll see very oftentimes a plot of intensity versus angle. Intensity could be in radiant terminology, or it could also be in luminous intensity terminology. That's flux per unit solid angle. Anyway, don't worry about those units. Just look for the plot where it says intensity versus angle. And if you see that the plot looks such that it's symmetric, and at the center there's a peak intensity, and if you go out 60 degrees and the intensity drops by about 50%, that's roughly Lambertian. A Lambertian source will have that kind of property. And optical engineers love that distribution because the mathematics is very simple with Lambertian sources. So assuming you've got that kind of LED source, we're looking at this diagram sideways. I'm putting the camera's pupil, the camera's iris, on the side here. I'm putting the object you're trying to illuminate on the left side here. And you've got a source. If you point the source directly towards the screen, obviously right here at this position, you've got the highest intensity or irradiance, and it drops off symmetrically here and here. So there's oftentimes an attempt, if you're not an optical engineer, there'll be an attempt of you to try to tilt the source towards the object. But what you'll find is that if you tilt the source in such a way that it points directly at the object, at the center of its axis, you will not find that the peak intensity is right there. It is actually more towards the top here, right? By pointing the source directly at the center of the object, you will not get the brightest part of the illumination at that center. It's not obvious. What you have to do instead is you have to point it farther down this way to bring the center peak intensity right at the center. And it's given by this equation. The reason for this equation is because when you've got the light source pointing normally at the plane of incidence, you've got this cosine to the 4th power kind of drop-off. But if you tilt it, you've got a cosine to the power of 3 times the cosine of the difference between these two angles. And this equation tells you that if you point the angle beyond the theta naught, beyond this line of sight, you can balance all these terms here and create symmetry about the axis on the object. It's very nice, right? You don't have to do this if your light source is very big. If it's very big, you're filling the whole area here quite uniformly. But if you've got a small source, which is what the intention is in this presentation, then you've got to do this tilting process. All right. So, but one issue here is that potentially is that if you've got just a source, just the LED and the screen, you may not have a very bright profile. It could be fairly dim because you only got the LED. To make it brighter, you need an optic, like a lens, to concentrate more photons onto your scene. If you do that, you'll end up again with this kind of weird profile. But if you take your lens and your LED and you choose a pivot point somewhere between the lens and the sample plane or the region of interest, and if you rotate in a direction shown by this arrow, you can again bring the peak of the distribution towards the center. This is talked about in a patent of mine and my colleagues. I'm the primary inventor here of this patent, but we worked together on this patent. It was issued a couple of years ago. So let me give you an example of this. You've got the set of lenses here and LED shown at an angle. This is about 20, I think it was 21 degrees or so, somewhere between 20 to 27 degrees of angle. And you shine it onto the plane here, but there's a special position here in which this whole luminaire or light source with optics, that's what we call luminaire, tilt about some pivot point over here, and that brings the center right to center of the illuminations right towards the center of the axis of the imaging system. It's counterintuitive. You would think that you want to change this angle here, the angle of incidence, but you don't. You keep that constant because you need this light source to be away from this camera, right? What you do instead is you tilt the entire luminaire about that pivot point somewhere in between. Okay, so that works, which is great. You get a symmetric profile, but not exactly flat and uniform. Right? I mean, it's quite okay, but not significantly uniform, not significantly flat. So what is a way to make it really, really flat in illumination at an oblique angle? All right, so here's one trick. If you look at a book written by Professor Jose Sacian at the University of Arizona, he wrote a very nice book, Introduction to Lens Design, published in 2019. You look at page 61. He talks about the exit pupil of a lens. What's the exit pupil? Exit pupil is if you've got an imaging lens, you've got an object, you've got an image plane, there's always an aperture in the lens, an iris. And there's always, if you look into the lens from the object, you'll see a kind of virtual window. That's the entrance pupil. Turn the lens the other way around, you look from the back, you'll see the exit pupil, which is basically a virtual window, sort of like a virtual image of the iris in the lens. Right, so the exit pupil of a lens will be uniform in distribution if the light source or the object that you're trying to image is Lambertian, and only in the exit pupil will you see that uniformity. And it doesn't have to be, the object doesn't have to be collimated in terms of where it's located respect to the lens. It could be an object far away, an imaging lens, and an image plane, and right at the exit pupil is uniform if the object is Lambertian. So let's extend that concept towards providing a top flat illumination at an oblique plane. How do we do that? Okay, first, reverse the lens so that the image plane becomes a light source plane. Make sure that the light source is very small. Make sure that it's got a Lambertian output. Make sure that the lens is aplanatic. That's one thing I forgot to mention earlier on. Professor Session says that if you've got an aplanatic lens, that's a lens that has 0 coma and 0 spherical aberration. It doesn't have to be exactly 0. All it has to do is have minimal aberrations in coma and spherical aberration. You'll have an approximately uniform distribution at the exit pupil of the lens. But if you put a small Lambertian source, like a small LED, the bifocal plane of an aplanatic lens, then the rays come out collimated, right? They come out parallel. It doesn't work for any lens. It has to be aplanatic. And then if you've got parallel rays, then if you have, then you've got uniform distribution. And what happens is at the exit pupil, it'll be uniform, but because the rays are collimated, then that uniformity will extend over a larger space. Additionally, if you tilt a plane of illumination, because every ray is tilted at the same angle, it'll be every ray on the plane will experience the cosine theta, the same cosine theta. So it'll still be uniform, all right? So let's see how that happens. Here I have done a very simple, quick design of what's called a DoubleGal lens. That most machine vision imaging lenses are of the DoubleGal type or DoubleGal variations of it. I kind of just redesigned this lens. I flipped it over, reverse it, put a small LED about 1 millimeter in size at the back focal plane. Get the rays out. At every plane here, it's uniform, flat, and including this plane over here, so you can see it's flat and uniform. Then you tilt it at 25 degrees. That's basically like having oblique illumination. You tilt the plane at about 25 degrees, you still get the uniformity, right? And it's extended in size because you have a tilted plane. And then look, if you tilt it at 45 degrees, it's still really flat, right? Still really flat, and it's extended again because it's on a tilted plane. The drop of irradiance here, it goes with the cosine of the angle. So for example, if you look at this peak over here, you have about 0.025 in relative units. Over here, you have about 0.017-ish. You get that because you take cosine of 45 degrees times this number here, and you get this drop. It has to be a drop. So if you want to compensate for the drop of intensity or radiance, you have to kind of turn up the LED current from the light source. But it works, right? It would work. Here is a more expensive method of doing this. If you take a microscope objective, which is normally aplanatic, because microscope objectives have to have very, very high aberration correction. To do that, it's got to have 0 coma and stereospherical aberration. However, that said, some modern microscope objective lenses are not that well corrected by itself. It is corrected with a tube lens, so-called tube lens, right? Together, it's aplanatic, but by itself, it's not. But some are quite well corrected by itself. You take that microscope objective lens and you reverse it. Here, I have an objective lens that I got from a patent. I just kind of re-optimized it, reverse it, put a small LED at the back focal plane, get the light source to come out, and you'll see uniformity. You see this kind of like a slope here because the source is not that small relative to the microscope objective. If you make it smaller, you could get this to be more of a vertical. But in any case, within, say, a region of interest that's smaller than this extent here, you can see that's pretty flat. And then you tilt it at 25 degrees, it's still flat. Till at 45 degrees, it's still pretty flat as well, right? It's expensive because it's a microscope objective. It's like $500 or $1,000 for an objective lens. Imaging lenses can be much, much cheaper than that, right? Okay, great. So you've got this method of having oblique illumination, and it's on a tilted plane, and your illumination is flat and uniform. But there are some disadvantages to using aplanatic lenses for doing that. First of all, if you want to illuminate a larger scene, then the lens has to be larger. As shown here, I've got the scene here. If I want it to be even bigger in illumination, then I have to increase the diameter of this beam. That means you're going to increase the size of the lens. That's going to be expensive. The other disadvantage is that, and this is not very obvious as well, if you plot structure across the light source, you'll see structure over the beam in the illumination. In fact, those of you who have tried this, you take a large size white LED. White LED is white because white LEDs, high power, large size white LEDs consist of many, many blue LEDs or UV LEDs line up in an array behind a phosphor screen that they illuminate, and the blue coming out from the phosphor screen and the broad green emission coming from the phosphorus or the fluorescence from the phosphor screen, the combination gives you white light, right? But if you look through the light source, you can actually see those individual LEDs. You put that LED at the back focal plane of a lens and you collimate it, you'll see structure in the beam, right? That's because of these individual beams from the LEDs, they overlap and they cause some kind of superposition pattern in the far field. So you don't want that as well. That's non-uniformity. Another disadvantage is if you have an aplanatic lens that creates uniform illumination in the collimated beam, if you want to beam expand that or beam contract that, if you want to project the beam over a larger space, then every other accessory beyond that lens has to also be aplanatic, right? And that can be problematic, right? So there's some disadvantage of using aplanatic lenses. Okay, so going through all the choices there, what other options do we have? Well, okay, so if you don't want to deal with those disadvantages that I mentioned earlier, there's still another option here. The idea is to make use of a multi-lens optical system, and I call it a multi-lens optical system because a system like this is multi-element, but not multi-lens, I guess you can call it. I mean, we don't have to be too strict on the definition, but this is more like a multi-element lens system. The multi-lens optical system would be something like you got a bunch of optical elements here, a light source, and a separate imaging system or projection optical system. And you focus the beams in such a way that they end up being at a point here, but they diverge onto the plane of illumination. If you have this kind of configuration, then if you want to illuminate a larger plane, yeah, you may have to move this optical system farther away, but the size of the optical system remains constant. So doing it this way, you can illuminate a larger area with a diverging beam. And if you have a specialized system to create a flat top illumination, you can create a flat top illumination here at normal incidence or at an inclined plane. To do this, what happens is you have to create a special optical system that creates flat top illumination somewhere in between the two lens systems. And then you got to use a second lens system, which is a projector, to project that illumination onto the screen. So what kind of optical system can create that kind of special scenario for you? Well, it turns out there is a module out there called the Illuminator Module that creates a flat top illumination right somewhere here. And this is called the working distance from the Illuminator Module, from the front of the module. And you take a projection lens, you project that area out onto the plane of illumination, and you get this flat top beam here. And if you tilt the entire system by, let's say in this simulation, by 25 degrees, and you have to do something else special to this optical system, you can create a situation where, although the irradiance drops because again you've got the cosine angle effect, you can still maintain the uniformity. And you increase farther to about 35 degrees, which is the limit of what we can do right now with the Illuminator module. You get still the flat top distribution, but of course reducing irradiance. Right? The simulation looks very good, but as you'll see in the next set of images, the data shows that at 35 degrees, you get some weird distribution here, which probably is an effect of aberrations. In any case, this is a prototype experimental setup. You got projection lens and Illuminator module with something that we're doing in this system here that we are not able to show right now. So everything's in a kind of a black box. You project the beam out and you've got a flat top distribution over about 80 millimeters, which is pretty good, sizable area. And then you tilt the plane at about 25 degrees, you get this, maintaining this flat top distribution. It's a little bit of a wave here, but it's pretty good. Otherwise, in ordinary terms, it will be very, very asymmetric, right? Very non-uniform. At about 35 degrees, you get some small variation here and some drop over here. But for the most part, within about maybe half this, 40 millimeters to 45 millimeters, pretty good flatness profile as well. So it's possible to produce this kind of distribution using the module and the projection lens. What's also interesting is that this is a scan of the distribution in this dimension, left, right, horizontal dimension, but there's also a distribution in the other dimension. So for example, here again, I repeat the images that I showed just previously. You scan across in this direction, you get flat and this weird small drop off here. But if you scan in the other dimension, when you tilt it at 25 degrees and 35 degrees, you see this kind of a concave distribution. Well, depending on what your definition is of top hat distribution, some top hats may have this kind of dip in it as well, right? In any case, it looks like we still have some work to do. It turns out that probably we would have to find a average distribution where if we make an adjustment to this optical system, chances are this will end up at around, let's say around 25 degrees incident angle. This will end up somewhat dome shaped, like a little bit of a slope at the edges, but symmetric, and this will be flattened out, probably something like that. But in any case, at least we can see that creating this kind of flat distribution on an inclined plane and over an extended area is indeed possible. All right. So what are some of the applications of this kind of setup? Well, as mentioned earlier, if you have just a single source on one side of the camera that you're using for imaging, then on all other areas surrounding the camera, you can leave space for other kinds of special components if you need to. So it could be in industrial inspection onto flat, and it has to be flat surfaces and or such as wafer surfaces, for example, or maybe circuit boards, anything that's flat. If you're rounded, if you're kind of like a sphere or have a surface that's kind of wavy, then you will not get the kind of uniformity, even if you use the aplanatic lens method, right? Because if you use the aplanatic lens method, for instance, in this scenario, you only get the constancy in the angle on a flat surface. If you got a wavy surface, you got a weird wavy cosine effect. So you will have that waviness of the surface will end up with waviness on the illumination as well. So it has to be somewhat of a flat surface in the application. If you mount such a light source onto a surface such as a magazine cover or a book that you're trying to scan with a digital scanner, that can work as well, as long as you flatten out the page. Well, the page probably doesn't have to be very, very flat. It just has to be somewhat flat. I mean, if you're reading a book, you won't notice the gradient in the illumination very much, right? Another application is quality inspection. In quality inspection, if you want to look for dirt or contaminants, usually you would use fluorescence imaging, right? A lot of contaminants are fluorescent. So if you mount a filter wheel over the Illuminator module and its projection lens here, and you mount another set of filters over it. In fluorescence, we call it the excitation filter and the emission filter, because in fluorescence you have to excite an object for it to produce fluorescent imaging. And to see the fluorescence, you've got to cover the camera with an so-called emission filter, and you got to cover the light source with an excitation filter. These filters have specific band passes to them in terms of the spectral transmission. But if you do that, then you can create a fluorescence imaging system with very flat illumination. So these are the three main applications. Probably there are more that I can think of, or we can think of for now. And with that, in fact, I'm pretty much done. And I would like to thank my colleague Li Hao Tan for the experimental results of VBMB, and also thank the team and my colleagues at VBMB for their continued support. And that is it.
Thank you so much, Bronian, for joining us to present on uniform illumination for machine vision applications. Before we wrap up here, I just want to remind everyone in the audience, if you haven't already, you can type your questions and comments into the conference chat box, and do not worry, if you have not been answered yet, you'll be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the 4th annual Vision Spectra Conference. Thank you all so much for joining us.